acceleration. What is acceleration? Is anytime you change velocity. Now, you should be careful with acceleration. It's really easy to mix up acceleration with velocity. In fact, there's a lot of people that will mix those up. I will try to do my best in trying to explain what is actually happening. Okay, so let's go.
I have a question.
Sure.
Like, so you're saying change in velocity, so would that be a change in a decrease in velocity as well?
Yes.
Okay. Thank you.
Yeah, anytime you change the speed, whether it's speeding up or slowing down, that is a change in velocity. Anytime you change direction, that is a change in velocity. One of the things that we have to worry about is in everyday language, we're sloppy. We say acceleration, but most people think of acceleration of speeding up. And you'll see that when I define it physics-wise, acceleration by definition means change in velocity.
Okay.
And so I'll try to separate them out to be as clear as possible. So here we go. So anytime one changes velocity, one accelerates. And so what that means here is it really means this. I can either change speed while being at constant direction, or I could be at constant speed while having a change in direction. You gotta be careful. Many people say that acceleration is only about changing speed. That's not true. That's half the truth. So what we do then is that in physics, and here's where the language of every day is different from the language of physics. So in physics, when we say acceleration, we mean one of these three possibilities. I'm either speeding up, and what we typically say in everyday language is we say we're accelerating. We could be slowing down, but in everyday language, we say decelerating. Or we could be turning. And when we're turning, what are we doing? What we call this is that we call this centripetal acceleration. It's the acceleration, it's turning acceleration. So you gotta be careful with the language. So remember, this thing in red here is everyday language. But that's not what we say in physics. As you'll see here in a little bit, how we define acceleration is actually the direction of the acceleration. And it makes complete sense once we start drawing the vectors of acceleration. Okay, that's what we want to look at. So now what we want to do here is that I want to remind you acceleration is a vector just like velocity. So what does that mean? That means it has magnitude, length, and direction. So we need to talk about both of those things. Okay, we need to talk about both of these things, not one of them. So let's talk about the first one. We want to talk about the magnitude of acceleration. So if I look at the magnitude of the acceleration, what are we doing here? So it looks something like this. It says this. It says that acceleration is how quickly one changes velocity. And what we typically do here is that we write this as an equation. So what we say here is that we come over here and we just say, okay, acceleration is equal to what? It's equal to the change in velocity over the time interval. Equation-wise, we try to make it a little bit simpler. And what we say here is that we say that acceleration is then what? The change in velocity over the time interval. So when I write this down, this is what I mean by the magnitude of the acceleration right here. And believe it or not, you have a really, really good feel for this. Okay? You have a really, really good feel. All I'm trying to do is use your intuition to answer these questions. So what I want to do here is that I want to go in and I want to get a feel for what's actually happening. So typically what happens here, to give you a sense of what do I mean by acceleration here, is that I want to go in and I want to give you an example, a situation. Okay, so we're looking at a situation of a car slowing down. So you could imagine that we have two cars. They're the exact same car. The only thing that's different is that they have different colors. So I imagine that I have this car, which I'll say is my red car. And this car is going this fast right here. So I know it's going that fast. And then of course, this thing is on a blacktop right here. And then I want a green car. And the green car is identical and it's moving exactly at the same speed. So if I look at this car, I'm imagining this situation right here. And this car is traveling at exactly the same speed. And what they're driving towards is that they're driving towards a stop sign. So we have a stop sign over here. And so of course, this is a red stop sign. And we should probably write a little tiny stop. And what we're going to be doing here is that the situation of a car slowing down and stopping at the stop sign. So if you're driving this red car, and what you're going to be doing is that you're going to be slowing down over this interval here. Okay. So eventually what we have to do here is that we have to stop the car. So each car is going to have to stop. So each car must stop. So that means here is that the change in velocity of the red car must be equal to the change in velocity of the green car. They start with the same speed. They end with the same speed. So their changes in speed is exactly the same. But there's something different with the green car. So the green car, the red car are moving. In the green car's lane, a little person, a little boy or a little girl, they run out into the street. Now, I'm assuming that if you're an upstanding citizen, you're not going to continue to move the car at that speed that you're going. You're going to hit the brakes and stop. So what you're finding here is that in this situation, the green car has to stop quickly to avoid hitting this little person here. And so what that means here is that the time interval has to be smaller. So they're changing their speed over a much smaller time interval. On the other hand, the red car takes longer to stop. So when I look at the time interval for the red car, since there wasn't a little kid running out into the street, their time interval is very, very large. So let's go look at the acceleration. So when I look at the acceleration, what I said here is that the red car changed its velocity over a longer time. So if I do that, what does that mean equation-wise? It means this, that I know that the change in velocity of the red car is exactly like the green car. What's the difference? The red car took a long time. So if I have a big number under the denominator, then I get a smaller number. Therefore, this means that this car, no, not this car. The red car has a smaller acceleration. It took me longer to change my speed. But if I do the same thing for the green car, green's car changed its velocity over what? A shorter time. So note, if I look at the speed of the green car, it should be exactly the same as the speed of the red car. But the big difference here was what? It had a little tiny time. And if I have a small number under a denominator, then that means I had a higher acceleration or a higher deceleration. So therefore, we say that the green car has a higher acceleration. But in everyday language, people call it what? Deceleration. Deceleration. Well, so the question is, the acceleration again is telling us how quickly we're changing speed, in this case, or velocity. And what do this little red acceleration mean? What does this big green acceleration mean? You have a very good feel for what I'm talking about. So let's answer that question that I just posed. What does it mean for a small versus a large acceleration? And the answer is, every time somebody accelerates, you feel something acting on you. So whenever one accelerates, and I got to be careful here, you feel some kind of force acting on you. And the word force is very misleading. I should not use the word force, but I don't know a better way to communicate that. It's not a force, but you feel something. What you feel here is either a push or a pull. So think about what happens here. Okay. So if I think about what happens, let's think about these examples. Let's think about the red versus the green. Okay, here we go. So as some examples here, here's going to be my first one. My first example here is that you perform a hard braking while driving. Right? So this would be like the big green one right here. So what happens when you perform a hard braking? Your body feels as something is pushing you forwards. And you probably have the instinct that if somebody's in the if somebody's in the passenger seat and you suddenly hit the brakes really hard, you may note that your arm may go outwards, especially if that person is smaller. So when this happens right here, you're changing your velocity because you're stopping quickly, right? So in this scenario here, we're literally saying here is that the most common thing here is that you get this little tiny time. right? You get this little tiny time for stopping. So therefore, you get a huge acceleration. So in most cases, what you're seeing here is that this is a small stopping time. And that's typically the way that we see acceleration when driving. Of course, there's the other situation that we could have. When you speed up quickly, right? If you speed up quickly, what happens then? Your body feels as if you're being pushed backwards. Into your seat. And so when I look at that scenario here, the fact that when you're being pushed back into your seat, what are you doing here? You're changing your velocity because you're speeding up quickly. Oh, I missed an I here. Let me put that in right there. You're speeding up quickly. So that picture tells us then, in this situation, you could then be going also a little tiny time here. And therefore, you get that big acceleration. Again, here, this would then be what? This would be a small speed up time. So I can accelerate two different ways. I can speed up or I can slow down very quickly. And the other thing that also occurs here in the third situation, remember, if you change direction, you are speeding up. You could be turning quickly. So if you're on the fish hook and you turn very, very quickly, what actually happens? Your body feels as if it's being pushed towards the door. So if you're being pushed towards the door, then we say that you're changing your velocity by changing your direction quickly. And this one's harder to write down because now you have to look at the direction part and we can't write it just like we've written it before. So we could then summarize this, right? The quicker you change the velocity, the stronger the push. So in summary, we could say here is that the quicker you change velocity means that you get a stronger push. But if you get a stronger push, that means that you have a higher acceleration. So if I now do it slower, then I'm going to get a weaker push. And if I feel a weaker push, I then feel a lower acceleration. So this guy summarizes what we mean by the magnitude of the acceleration. This is how you can tell what that acceleration is. So now there's another piece to the magnitude of the acceleration. And I think I have to talk about it right now. Okay, but that's physically what it means. So now the way I'm going to look at this thing, actually, I'm debating whether I should put this in now. So if you're driving at constant velocity, what we say here is that your body does not feel anything. It's not being pushed at all. So what we say here is that because it's not being pushed, we say that the acceleration is 0. So guess what? I'm going to come in here and I'm going to say acceleration is 0. Your body doesn't feel anything. Now, let's go put in the cars. Now we're going to do exactly what we talked about before. We talked about speeding up or slowing down, speeding up, and then we're talking about turning. So let's look at these 3 situations. So in this situation, I'm going to talk about braking. Speeding up. Turning. And remember, these 3 cases are the case that we just did, right? A hard braking, speeding up, turning. That's why I have these cases. So then I'm going to feel my body. So in each situation, you see that the car has a velocity to the right. Now, if I brake, which direction does my body go? So if I brake, I know that this direction, my body moves forward. So if my body moves forward, the acceleration must be opposite of the velocity. It's opposite of the body's direction. Now, if I'm speeding up, we feel that our body goes in which direction? It's like being pushed into the chair. So our body goes in that direction right there. Therefore, the acceleration must be what? In the opposite direction. And when I'm turning, it feels like my body goes into the door. So this is hard to draw here. So what we're going to say here is that your body is sort of like going into the door. So what happens to the acceleration? It turns out it's got to be perpendicular to that. So then the acceleration is perpendicular to the velocity. So in summary, this is what we could say. If you're moving at constant velocity, what happens? Constant velocity says my velocity vector looks like this. My acceleration is 0 because my body doesn't feel any force acting on it. But then what happens? If I'm speeding up, I then see that the velocity and the acceleration are in opposite directions. Ooh, Boy, did I say that wrong, didn't I? I meant to say slowing down. So let me write slowing down. And then if I'm speeding up, then I see that the velocity and the acceleration are pointed in the same direction. And if I'm turning, it turns out that I can do two things here. So it turns out that if I go in this direction, and the acceleration in this case is perpendicular and to the right, this guy is going to be what? This is going to be a right turn. On the other hand, if I have it the opposite direction, where the velocity goes like this and the acceleration goes up, this guy is a left turn. So when you look at this thing, you could see, what do I mean by acceleration? When I look at acceleration, if I'm slowing down, speeding up or turning, it's the direction of acceleration. So a lot of the times, this is what we say. We say that when we say the word deceleration, this is really what we call negative acceleration. It works against the velocity. In everyday language, when we say we are accelerating, we call this positive acceleration. But you could see that it's really just the arrow that's happening here. And here, when we call this turning acceleration, what you're seeing here is that this is perpendicular acceleration. So anytime the acceleration is perpendicular, you will be changing directions. Anytime the acceleration is either against or with the velocity vector, you will be slowing down or speeding up. And anytime when you have zero acceleration, you do not change your velocity at all.